Good morning. So, there is a question which connects the real life with an abstract life. Well, there are always things in our life which we wish we could change, but we can't. Like some of you would like to have an instructor with a different accent and handwriting, but that's not going to happen. In physics, there are much more important things which we can't change. For example, right-hand rule. And what is a corkscrew? Just a regular right screw which moves in a certain way. So everybody had at least one experience with using a screw. If you look down and you rotate it clockwise, that's what's called screwing in, which means it will move away from you. And if you start rotating it counterclockwise, you will screw it out, which means it will be traveling toward you. So a screw relates rotational motion with a linear motion in this way. Well, a standard right screw has a thread which makes it move in that way. The first person who used screws a lot was Archimedes for lots of things. And now you have to make a transition from this everyday experience into this abstract situation. And well, you have to imagine, first of all, what would you see if that would be you looking down at that corkscrew, which rotates clockwise. And then that motion should be viewed again by you from a different point of view and related to X, Y, and Z axes. And there is no other way to do it. There is no other way. Doesn't exist. So, if you would be looking down, relative to you, this corkscrew moves clockwise. So, and by doing that, you are simultaneously two persons, one person who's looking down, and second person who's looking at that person looking down. So that would mean this corkscrew would be moving away from that person, away from that person, from a person, for a person who is looking at that person. That motion is not away, that motion is down. And down for this person means what? Negative X. Why would I point X up? Because I can. This is X, Y, Z reference frame. The mutual orientation is fixed by the way it's built. It's a right frame, and the relationship between X, Y, and Z axes doesn't depend on how we hold it or how we look at it. So we can use any type of the orientation. So down opposite to X, that means negative X direction. That's how it works. That's it. And I'm not sure if any in this room has experience of taking dancing lessons or learning how to play a musical instrument. But if you had that experience, you would know that in order to learn how to use an instrument or how to use your own body, first you have to memorize the description of those steps, the sequence, because it has to be in your memory. And then you have to use that sequence. So training is first couple of steps more, then the whole sequence, again and again. And learning physics is no different from learning how to dance tango or play piano or ride a bicycle. And here we have a list of different right-hand rules which we have to use to relate a specific physical object like a hand with some abstract concepts. And of course, that requires manipulating in our mind with a number of mental objects. And of course, if it's one or two mental objects, it's easier than it's 7 or 6 mental objects which should be manipulated at the same time. But it's all just a matter of practice. So just a quick review. Force acting on a wire from magnetic field. Force acting on a charge from magnetic field. And this is the new one, but it's old one. It's how to relate area vector, magnetic field, and torque. All these right-hand rules based on X, Y, and Z axes together. In all these rules, we always have index finger, which an equivalent of X axis, magnetic field B, and whatever it is, Z, always. And here we have, at first glance, a different type of right-hand rule. It's based on how a corkscrew or general right screw would move if we would make it rotating. If you would use a screw here and would spin it in this direction, how do we call this direction? We don't. First, we have to make a statement relative to whom, because a person looking down and a person looking up will see it differently. From one person, it will be clockwise direction. From another person, it will be counterclockwise direction. If you don't say specifically how you look at it, and you know, the motion is relative in physics, everything is relative to specific observer. So if you don't specify that, there's no name. But for example, if you, well, it's just a force of habit. If you look down and it spins like this, the corkscrew relative to that person would spin counterclockwise, and that would make it move toward the person. And here and there, all the same rules. This is the corkscrew handle, and you spin it, and this is the thread, people call it worm, which move one way or another. The most complicated rule we've learned so far relates the direction of a torque with other variables, and it is a combination of PY105 and PY106, and from PY106 we've learned that we have to define area vector. How do we do that? Another right-hand rule. And if we define it, and then we look, that it would move. Why? Because it wants to. Because torque is acting on it. It would move if we let it move toward the magnetic field by the shortest path. That motion is related to a specific direction, has been defined out of the screen or into the screen. But we also can use three directions: area, vector, magnetic field, and torque, using the reference frame, because they're related. If you take the reference frame, X, Y, Z axis, the right one. There's a left one, we don't use it. And if you spin X axis toward Y axis by the shortest path, the corkscrew would move in the direction of Z axis. So they're related. And now you can just forget everything I said and just practice using right-hand rule depending on the situation. For example, this situation. It's a long question, so I'm going to give you time to read it. Also, you should choose your answer wisely. Don't choose 8. It's better just guess than give up. Even 7 is better than 8. So again, there are two persons, two observers which communicate, or the same observer which simultaneously at two places looking at the same object from different views. You looking like this, face view, and another view looking straight down. So when you look and you see the whole loop, relative to you, electric current travels clockwise. And when another you looking down, relative to that person, this loop begins spinning counterclockwise. So for a person looking down, this loop begins spinning like this. This is what it is. For the person looking down, it starts spinning counterclockwise. But relative to you, if you come back to your seat and you look how it spins, it's going to look like this. And you have to be able to imagine all of those views. Now, what's missing is area vector. So you need to add. How do we do that? We have skills. So this loop has the area vector. Is it right direction? No, it's wrong direction. This area vector points away because electric current travels like this or like this. We can use either right-hand rule just for a single wire or for the whole loop. So this is the direction of the area vector. By the way, after this class, this is for sale. So, and as we said, it will begin spinning like this. Okay, like this. Okay, I have a solution. Now we know that from rest, when it's released, it begins spinning by the shortest path toward the direction of magnetic field. Area vector wants to become parallel to the magnetic field. So only one of these possible answers tells how magnetic field should point. And again, we can also start from eliminating wrong answers. For example, this motion is happening in a horizontal plane. Magnetic field has to be horizontal, maybe left, maybe right, maybe out of the screen, maybe into the screen, but definitely cannot be up or down. If it would be up, the motion would be like this. If it would be down, the motion would be like this, because that's what it wants. Yeah. Magnetic field, area vector, let it go, it starts spinning toward magnetic field. And now, if it starts spinning like this, that's supposed to be the direction of magnetic field. Now, so what should we add? Well, the area vector, as we said, should be into the screen. Now, motion. Come on. So as we said, this loop relative to that person would start spinning counterclockwise. So this side would be moving toward us, or toward you. This side would be moving away. Technically, we will also have symbols for that. Toward us, that's velocity. Away from us, velocity. And this motion, like this, can be used in a combination with the right-hand rule to show the direction of a torque. If it's a physical object, which starts spinning like this. So our original right-hand rule says these fingers, if they show, well, technically they show angular acceleration, which is same as angular velocity, because we begin moving from rest, and so the thumb shows the torque, and now we have two directions, area vector and torque, and this is where we know, on one hand, magnetic field should point over there because A wants to become parallel to it. On the other hand, this is an opportunity to use first and maybe last time that new rule, which relates three vectors, area vector, magnetic field, and torque. Since we know two of these directions, the third will be given by this rule. And of course, okay, let's do it black. It's just, again, a matter of practicing. Trying. Yes? Can't hear you? Well, I can go only briefly about this because that is in the rule right here from PY105, how we define the direction of a torque. But in this situation, we take this picture and we turn it by 90 degrees. Well, okay, let's take quickly. at the practical applications of this stuff. Practical applications are very important for us because we use them. And people like Elon Musk make billions on that. Yeah. They use electric motors to move the car. So what do we see here is a single so-called DC motor. It has only one single loop, and this is the magnet, so it generates magnetic field. So it's very sensitive. Let's hope it's gonna work. All right, come on. Sometimes we need to give a jump. Oops, so I broke it. Well, even better, now I can take it out and hopefully show you. This is the rotor, and there's a little cut here and there. Why do we need to cut it? Because we have to change the direction of electric current in this loop every, well, at least half of turn. Otherwise, it wouldn't be spinning in the same direction. It would be oscillating back and forth, back and forth. So physics is simple, but engineering is actually kind of ingenious. Well, I have a backup. This is more like an actual motor. Instead of just a single loop, we have a coil, two magnets with opposite poles, and a battery. And again, we need to give it a jump start, maybe different. And it starts spinning. And again, if we look at how it's made. So there are two brushes, of course, which we need to connect the battery to the, well, rotor, but the rotor also has two halves. There is a cut here and cut here. So electric current travels in one direction, but then travels in the opposite direction to keep the torque in the same direction. Well, if you are curious enough, you can read more. Where? Anywhere. Wikipedia. Textbook. Well, so that was our last problem with two wires interacting. This is a review. And now let's just do a couple of more examples before we move into the next topic. Fine. Here we have five long wires. They all point horizontally, well, placed horizontally, and electric current might point toward you or away from you. Electric current in a wire at the center points away from you. And what we know is the net force acting from other four wires. And we need to figure out how can it happen. Well, that's where we use this rule. Parallel currents attract each other. So how, well, the first part is purely geometrical, it's geometry. If we have two wires, let's say number 4 and the middle one, depending on the electric current in the wire number 4, these wires might only attract or repel each other. So force, the individual force, can point only diagonally toward the wire 4 or away. So here in this picture, there might be only 4 individual forces, 2 along one diagonal and 2 along another. So we have to figure out how would we add forces like this plus this plus this plus this in order to get the net force which points toward the wire number 1. Well, in my example, the first two arrows together would give one longer arrow pointing toward wire 4. The second, the third and fourth arrows together would give this. Now we have to apply a tail to a head rule, a tail to a head. So now some people still might forget what to do after we have to connect, but that's not the only action which has to be done. We also have to add the arrowhead, and well, that blue arrow doesn't represent the arrow which is supposed to be. Yeah? So that doesn't work. Wrong. And now we have to just try again and again and again all combinations and see which would work. But of course, there is kind of an intuitive approach. We want to have two arrows pointing in this direction, because if they point opposite to each other, they would cancel each other out. If they point both in opposite direction, well, that would be just wrong. And here we want to have two arrows which cancel each other out. That's what we want. This is based just on geometry, vector addition. Now physics begins. Yeah? So how can we make that work? Well, attraction. So this should be parallel and this should be parallel. And attraction here, this should be parallel and this should be actually repulsion from this wire, so opposite. That's one possible combination. If we call them, so this will be well, let's call it 5. On 5 from 4. On 5 from 2. On 5 from 1. And now on 5 from 3. Is it the only possible combination? What do you think? Can I change the direction of a current in the wire number 1? No, I can't. It would begin repelling. And I cannot change the direction of a current in the wire number 3. I can't, because, again, that wouldn't give the right direction. But I can change the directions of the current in the wires 2 and 4. So I still keep this, I still keep that, but here, now if they both are out, forces still will cancel each other. So this is still F5.1, 5.3, but now this will be force on 5 from 4, and this will be force on 5 from 2. They just flip, but still cancel each other out. And again, this is just an exercise in vector addition more than in physics, plus the rule, which we have to know. And of course, we can calculate the force if we know everything. For example, well, first of all, with not calculating force acting on a wire in this example, we are calculating force acting on 1 meter of that wire. So what we, what we need to calculate is this ratio, which is equal to 4 pi times 10 to the negative 7 times each electric current is equal to 2 amps, so 2 times 2 divided by 2 pi. Now, we need to know the distance, and we have to multiply by 2, because this net force is composed of 2 individual forces which point in the same direction. That will be the answer. Now, the distance. The length of each side of this square. What a weird number. Why would people do that? No, we cannot call it L. We can call it A, and that equals square root of 2. So D will be equal to 1/2 a diagonal, and diagonal will be equal to square root of 2 of square root of 2 squared plus square root of 2 squared, which is, I want to believe it's 1. This is when our beliefs come true. That's it. So what does it give us? Pi and pi canceled, 2 and 2 canceled, 2 times 2, 4, 4 times 4, 16, 16 times 10 to the negative 7, right? Pi and pi, 2 and 2. That's it. Again, it is more on vector addition problem and more on geometry. Yes? This? Yes. Of this, because net force is the sum of 2 individual forces which are equal. One more example, of course, again, 95% is geometry. But I have to do it so people wouldn't say that I didn't do it. We have a third wire located here. And that electric current travels into the page because we can read. Now, it means that it's being repelled. So this distance is equal to 2 meters. This distance is equal to 2 meters. Distance is the same, but the current number 1 is stronger, so the force will be stronger. Now we got to do a different type of geometry. But first, we have to calculate now each force. On 3 from 1 per meter. So, okay, 4 pi 10 to the negative 7th current number 1, current number 2, 2 pi times 2. On 3 from 2 per meter, 4 pi times 10 to the negative 7. Oops. Now it's a different current times 2 divided by 2 pi times 2. Well, a tail to a head rule says that the net force will be equal to the hypotenuse of this, well, the net force per meter, that's what we're calculating, will be hypotenuse of this triangle, so it will be equal to. Now, you have to follow my work because I might make a mistake because I'm doing some calculations in my mind. For example, I know that these two numbers have common factors, and if I square it and then take a square root of that, it will become the same factor. So what is a common factor? Well, pi and pi, 2 and 2, pi and pi, 2 and 2, 4 over 2, which is 2, 10 to the negative 7th, and this 0, which represents another 10. And what's left inside is 3 squared plus 2 squared from this number 3 and from this number 2. So 2 times 10 to the negative 6 times square root of 9 plus 4, 13. Now I have to take a calculator. Square root of 13, 3.6, well, times 2, 7.2, 7.2, 10 to the negative 6, a Newton over a meter, actually. That's the unit. A Newton over a meter, because that's what we've been calculating. Force acting on 1 meter of that wire. Well, we have done this type of calculation so many times, so by now we should be familiar with this type of reasoning. The only new thing is how we're calculating force, and that depends on the physical system. If we have 2 wires, that's the equation. If we had 2 charges, that would have been a different equation. Question, which moves us to the next topic. And I have an experiment which will allow us to test our predictions. So we have a conductive bar. Aluminum is a conductor, which is moving to the right with a constant velocity in the magnetic field, which is directed into the screen, or we can say away from you. What does every conductor has? It has electrons which can freely move inside. So each electron should begin experience a force because it's being moved, and that force should start acting on those electrons. So they will be moving as a whole in a certain direction, and because of that, they will be collected on one end of this electrode. So another end of this rod, electrode, bar, will be missing electrons, and that will make it positive. This is the aluminum bar. This is the magnetic field between the poles, north-south, leaving north, so points away from us. All we need is a device to register the presence of, well, if one end becomes positive and another end becomes negative, that's what we used to call a battery. So a moving rod like this should start acting like a battery. And to measure the voltage of that battery, we need a device. We call it voltmeter. But, of course, in this experiment, the voltage will be so low, so we need a very sensitive voltmeter, which has a different name, a galvanometer. But still, it's just a voltmeter. And we have to connect it to the rod. And for now, nothing really happening. Electric current, well, actually, magnetic field of the Earth generates electric current. So, but it's so low, we cannot measure it. Now, let's see what's going to happen if I make it move through magnetic field. Did you see it? It moved. And now, see what's going to happen if I move it in opposite direction. It moves in opposite direction, which means when I move it down, this actually becomes positive, this negative. When I move it up, they flip. So velocity, magnetic field, and polarity related. How? Well, that's what you were supposed to figure out. And the answer is in the right-hand rule acting on electrons, which makes it left-hand rule. All we have to do, draw a single electron which is being moved inside the bar. Single electron, like this guy. The velocity of this electron is provided by, well, the velocity of the bar, and the velocity of the bar may be provided by our hand, which makes it move. Or it might be just falling down through magnetic field. And now we have to apply the left hand, or use the right and then switch the result. But it's just easier using the left hand. That's the velocity of the electrons. What's wrong with this orientation? Magnetic field, it should go into. So this thumb shows force acting on those electrons. Those electrons will be moving down the rod, and it means here we will have more electrons, but those electrons will be leaving the top end. So this rod becomes an equivalent of a, well, battery. And this process doesn't happen forever. It stops at a certain point. When? When does it stop? It stops when the equilibrium is reached. And what does it mean? It means if we look at the electron, it is acted upon down by magnetic field. And the magnetic force has magnitude, well, Q, V, B. But as long as electrons moving down, we have electric field, which points from plus to minus, from high potential to low potential. And that generates electric force acting on the same electron, which equals Q times E, well, magnitude. And eventually, the magnitude of electric force becomes equal to the magnitude of magnetic force. That is when equilibrium is reached. It happens for a fraction of a second very quickly. And the equation tells us QVB should be equal to QE, and the charge is getting canceled. And that gives us the relationship between speed, magnetic field strength, and electric field strength. But if we go back in time, the potential difference, electric field and length are related. So, the length of this rod, the potential difference divided by this length should be equal to the magnitude of that electric field. And that is how we get this relationship. We don't really care technically about the strength of electric field. We cannot measure it directly, but we can easily measure directly voltage. That's why we need it. This voltage also has a different name, EMF, electromotive force, because it starts acting like a battery. So a different name, a different letter, but basically it's the same thing. So if we start moving faster and faster, we can induce higher and higher voltage between the ends of that conductive rod. In a stronger magnetic field, it also generates stronger EMF. This EMF has a special name, motional, because it's induced due to the motion of a conductor through magnetic field. That's it. So if you hear or read motional EMF, as I have been saying for 16 years, don't become emotional. It's just an equation. Now, of course, we have to connect it to something and see what's going to happen. So we saw this experiment. How do we check it? Well, we do the experiment. And another quick note. In our calculation and our experiment, all three directions were perpendicular to each other, like x, y, z. What's going to happen if it's not the case? Well, you just have to use components which are perpendicular to each other. That's it. Because parallel components don't matter. They don't affect. And if a magnetic field or velocity have no perpendicular component to each other or to the bar, that number becomes 0. There is nothing induced. So we have to have all three directions at 90 degrees to each other. Well, first of all, of course, the bar. Second, velocity of that bar. And third direction is magnetic field. As long as magnetic field and velocity have components perpendicular to each other and to the bar, the EMF is induced. Well, question, what's going to happen if we make a circuit with this particular battery? How do we make it? Well, this is how we make it. Two conductive rails, a bar connected to a bulb, magnetic field, and starts making it move to the right or to the left. In this experiment, magnetic field again points away from us. The same aluminum bar is being moved in the same direction to the right. But now we complete a circuit using a resistor. And if we have a battery and a resistor in a closed circuit, there has to be electric current. And electric current travels in the circuit either counterclockwise or clockwise, which means electric current through this resistor travels either down or up. Electric current through the rod, of course, travels down or up. Electric current through conductive rails travels left or right. Of course, rails are ideal, have no resistance, and the bar has no resistance. If we have any resistance, it's there in that resistor. So direction of electric current through the resistor. Okay? To answer that question, first you have to make a statement about the direction of electric current in the circuit. Is it counterclockwise or clockwise? What do you think? Clockwise or counterclockwise? So if you think electric current is clockwise, please raise your hand. If you think the electric current is counterclockwise, please raise your hand. Why? Exactly. So the bar becomes acting like a battery. That's what we need to remember, which means we literally can replace it in our mind or in our picture with a battery, but that battery has to have the correct polarity, plus and minus. So how do we know which is which? we have answered that question already, right? We don't have to use the left hand and talk about actual physical particles, electrons. We could talk about fictional positive particles, positrons, and use the right hand. Those particles would have been moving to the up end, to the top end. So again, this end should become positive, this end should become negative. That makes a battery look like this. A positive and negative electrode, and that makes electric current travel from plus to minus outside of the battery, which makes it counterclockwise, which makes electric current through the resistor traveling down. And you see, it's like juggling, but with mental objects. So that's the answer. Now we have to solve a specific problem, because now we have everything we need to solve a specific problem. We have that device, a loop, which has a resistor in form of a bulb, which has a battery in form of a rod moving through magnetic field. We know the magnetic field strength, we know the resistance of the resistor, we know the length of the rod, and what else do we know? 2 amps, what is it? At what speed do we have to move the rod to induce the current of 2 amps? Well, it's just when you read the problem and it has so many questions, it basically says, that's what it says. Anything you can, you should. So, well, the first step, of course, to analyze what is happening to it over time. And that actually makes a difference in certain situations. So, at t equals 0, it is not moving, velocity is 0, and then we start applying a force from our hand. That force has a certain fixed value. So, because of that force, this rod starts acting like a battery. And there is electric current in it. EMF will be equal to this product. But if the force is acting on this rod, it means it has acceleration, it means it's speeding up. So what velocity should we use? Well, the thing is that as soon as electric current starts traveling in the circuit, we also have electric current traveling through the bar, which is traveling in the magnetic field. So we have a wire with electric current in magnetic field. What does it mean? A wire with electric current in the magnetic field. What should it feel beside happiness? Force, Ampere's force, the very one we started this topic from. So there has to be now, this is applied force because of our hand, which touching this, holding and moving it. But as soon as the electric current starts traveling, there has to be Ampere's force acting on a wire from magnetic field. And if electric current points up and magnetic field points into the screen, that magnetic force should point to the left. But it is acting on the same bar, of course. So in reality, as soon as we started moving it, two forces start acting on it. One, the applied one, and second, from magnetic field. And eventually, if we move it, well, first of all, actually, we can mention that electric current should be equal to, well, voltage over resistance or EMF over resistance. Yeah. That's the Ohm's law. Nothing says we cannot use it. It's the same circuit. Yeah. We have EMF, we have a resistor, so we can use the Ohm's law. And the magnetic force acting on the wire from magnetic field is equal to, everything is perpendicular to everything in this example, so there's an invisible one, sine of 90 everywhere. This is the magnetic force. And the faster we move it, the higher EMF is induced, higher EMF, higher current, stronger force. So this force grows and eventually it becomes equal in magnitude to the applied force. And when that happens, when we have two forces which point opposite but have the same magnitude, net force equals what? 0. So eventually, and it happens very quickly, the net force acting on this rod should become equal to 0. And when it happens, when the magnitude of magnetic force becomes equal to the magnitude of the applied force, F net equals 0, that is when the speed stops changing. We have reached so-called terminal velocity, and after that it starts traveling at that velocity. And this is terminal. Which gives this electric current 2 amps. So actually, if we would be able to solve the equation for velocity, it's Newton's law, but with a changing force. So we would see that velocity changes from 0 to a certain value. The only problem is that we use the same letter for velocity in general and for that terminal velocity, which stops changing, which doesn't change anymore. Well, okay, so now, when it happens, what can we calculate? Well, we know the resistance and we know electric current when terminal velocity is reached. So we can calculate that EMF, which after that remains constant. 2 times 0.1, 0.2 volts. Now, what else do we know? Well, since we know EMF, we can use it to calculate that terminal velocity 0.2 over 2 meters over 10 Tesla. So 0.01 meter second. The applied force will be equal to that final value of the magnetic force acting on it. So the applied force will be equal to ILB I2L 2B10 40 newtons. The battery of which voltage can be used? Well, 0.2 volts. The equivalent battery should have the same terminal EMF. We just need to remember that when we use these calculations, we use final values when everything stops changing. Because EMF also changes from 0 when it was at rest initially to that final value. Well, answers 40 newtons. A different question. It's a different situation. You see, the previous problem had a bulb in it. Now it's not a bulb. Now it's another actual physical battery. It's a source. And I have it here. The power source. And what I do? Well, I have two conductive rods right here. And I want to place on the top another conductive, but not this one. Too large. This one. This is a big magnet. See? There's a magnetic field. So as soon as electric current will travel through this rod, force should start moving it in a certain direction. The only problem is, physics is easy. Making it work is hard. So we have to make a good connection. So we have to clean it up. And you should use this time to answer the question. When I close the switch, in that particular example, the magnetic field points into the screen. So when I close the switch, electric current will begin traveling in the circuit. How? Well, you should know this answer. So electric current through this rod will begin traveling in a certain direction. How? Well, you know. And then because electric current in a wire in magnetic field generate a force, you should be able to say, keep forgetting the magnetic field here. That should point up. So if I take this and I face it like this, magnetic field will point away from you like this. All right. Now, so that's a minus, that's a plus. So what should I expect if I read it correctly? Plus, 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 electric current, magnetic field. So I should expect that it would move. Let's see. One more thing. Don't forget to plug it in. It works. Physics always works. So, and your type of reasoning is exactly similar to my type of reasoning, because you know that electric current, if you close the switch, should begin traveling counterclockwise from plus to minus. So in this situation, electric current through the bar should point up and magnetic field into the screen. So exactly the same situation. It should begin traveling to the left toward the battery. So when the switch is closed, electric current should travel from plus to minus, which means, again, we should remember things we've used for the previous exam because they are being used again. Electric current travels counterclockwise through the bar. Electric current travels up. Magnetic field points into the screen. Right hand rule again tells the force should point to the left. I was right. Well, now, of course, we just have to solve the technically solve the problem like this. So you should read and transfer important data. Now I should read a copper. Why is it important? If it would have been a wood rod, there wouldn't be electric current. But copper is a conductor. So first I want to draw a bigger picture. We always need to keep in mind the bigger picture. So we have a rod. And again, first we need to consider what is happening at t equals 0. We just closed the switch. So electric current and magnetic field result in a force, again one more time, acting to the left. How do we calculate this force? Well, that's Ampere's force, current, length of the rod, a wire, magnetic field. But again, as soon as it starts moving, we now have a rod moving in the magnetic field. What does it mean? It means this rod immediately starts acting like a battery with its own EMF. Induced EMF. So this is an external EMF. But as soon as the velocity is not zero anymore, and velocity is not zero because acceleration is not zero, and acceleration is not zero because force is not zero, and that's Newton's law, PY105 lecture 4, we still have to remember all that. Induced EMF should be equal to the speed of the rod times the length of the rod times magnetic field strength. Now, that will give us an equivalent circuit with two batteries. We only have to make a statement. This, a new battery, will be connected plus to minus or minus to minus. And for that, again, we can use our right-hand rule. So now it is actually helpful just to look again at a rod by itself with the magnetic field into with the velocity to the left. Fictional positive charges would be here. right? No. Why do I do this? That's velocity. That's magnetic field here. Velocity, magnetic field. So this end would have become positive. Which would make this battery generating its own current opposite to the initial current. So if the rod travels faster and faster and faster, the induced EMF would be higher and higher. From zero, eventually it would reach the same magnitude as the external EMF. And what would happen? They would cancel each other. So eventually, the induced EMF over time, very quickly, reaches the value of the external EMF, but they connected opposite to each other. So eventually, they cancel, kill each other. And when it happens after that, there will be no electric current anymore, which is weird, but it will be traveling at constant velocity after that. By inertia, there is no friction. So it reached that velocity, net force again becomes equal to zero, and it just keeps traveling at that velocity. Kind of cool. All right, so what else can we do? Well, okay, so we know the external EMF, which means eventually the induced EMF, will be equal to the same value, 90 volts. What else do we know? The length and magnetic strength. Well, hence, if we want to calculate that terminal velocity, velocity changes from zero to that final value. It will be equal to induced EMF over length and magnetic field, 90 over 2 and 0.5, oops, 2 times 0.5, right? So 2 times 0.5, 190. Any questions? Of course, when we just need to solve a problem, we don't really think about the process which leads to establishing that terminal velocity, to that regime. We know it happens eventually, and we just write equations. Okay, so we know that when we have a conductor traveling in magnetic field, it starts acting like a battery. What's going to happen to a closed conductor? A closed conductor has a name, a loop. What's going to happen if we have a loop traveling in magnetic field? Well, we have to analyze two different situations. The situation number one, when magnetic field is uniform, and the situation number two, when the magnetic field is not uniform. It's more dense here, less dense there. So the difference is huge. And to figure out what's happening, we can look at two opposite electrons. So in the loop, for each electron on one side, there is electron on the opposite side. If we know what's happening to one pair of electrons, we know what's happening to all of them. And what's happening to these electrons? Well, if that's a magnetic field, that's a conductor. If I make this loop travel down The velocity of each electron is known. I make it travel down. And here, if we apply the right-hand rule, for each electron, we have the same magnetic field, same velocity. They will experience exactly the same force. Exactly the same means same magnitude and same direction. So one force will push this way, but another force will push the opposite way, and they will cancel each other out for each pair of electrons. In this situation, nothing will happen. Like magnetic field just don't exist. What's going to happen if magnetic field is not uniform? Well, the analysis is exactly the same. The velocity, which is the same for both. And now magnetic field is different. For example, here magnetic field is practically opposite velocity, which means this force, well, in this example, is practically zero. But here magnetic field has a very strong perpendicular component, yeah, B perpendicular. So this force now is much stronger. So they now cannot cancel each other, not balanced. And that means they should start spinning. They should start moving inside this loop. Moving electrons have a name, electric current. Which means if we have a conductive loop traveling in non-uniform magnetic field, we should experience electric current induced in it. First, let's see if it actually works. It does. All we need is a device which we can use to register EMF or electric current. Well, I cannot use this loop. I need something much more effective. I need many, because electric current induced in a single loop is very low. So I have to multiply by the number of turns. Here's about 400 turns. Now I need a source of magnetic field, not uniform magnetic field. So, and now we need to make this loop travel and make it in such a way so you would see it. Okay. Oh. Definitely electric current, definitely, which means definitely EMF induced. What's going to happen now? Again. So, what's going to happen if I do this? As long as there is no motion, nothing is happening. Change is badly needed to generate this current. What kind of a change? Well, if we look at these two situations, how do we describe magnetic field? Using magnetic field lines. So a uniform magnetic field, same number of lines, same direction everywhere. When a loop is traveling through uniform magnetic field, the number of magnetic field lines inside remains constant, the same. Here, it's different. Well, it's harder to see with aluminum loop, so I have the same loop. Now, how many lines are enclosed in this loop? Well, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. But if I move this loop away, now to enclose exactly the same number of loops, I need the larger loop. Which means if I have the same loop, the smaller number of lines penetrated, go through it. So when a loop travels through a non-uniform magnetic field, the number of magnetic field lines inside the loop changes. So no change, no current, no EMF. Number of magnetic field lines inside the loop changes. We observe EMF, we observe electric current. Of course, we also need to introduce a specific physical quantity And we will. But first, a conclusion. We can actually figure out the direction of electric current. The direction of electric current is opposite to the actual direction of the motion of electrons, you know, by definition. So if electrons start moving that way, according to a definition, we should say electric current travels this way. So this is a fact. Magnetic field doesn't change. No induced EMF, no induced current. Magnetic field changes. We observe induced current. So the fact number one about the rod, the fact number two about the loop. Now a loop starts acting like a circuit with a battery inside. Where is that battery? Maybe it's not there, maybe it's here. Just a picture, visual representation. There is no actual battery here, you don't see it, right? It's just acting like a circuit with a battery. The electric field induced inside this loop is not the same as we learned before. It's a different type of electric field. Well, how do we check the facts? We use experiments. We did it. And now finally, how do we describe it mathematically? To represent how much of magnetic field is inside the loop, or we can say the amount of magnetic field traveling through the loop, or we can say the number of magnetic field lines inside the loop, we invent, which means we define a physical quantity we call magnetic flux. Well, James Faraday did that. Michael Faraday did that. Michael Faraday invented this. This is an official definition of magnetic flux. What does it use? It uses same variables as before, but differently. This is magnetic field. This is the loop. To represent the orientation of a loop, what do we use? The area vector. So the orientation of a loop is described by the area vector. And magnetic flux is at the maximum. You can imagine like a flow of magnetic field through this loop. It's at the maximum when area vector is parallel to magnetic field. And when we turn it, magnetic flux decreases. And now there is no magnetic field through the loop. It is missing the loop. It happens when area vector becomes perpendicular to magnetic field, which is described by this equation. B is the strength of the magnetic field. A is the area of the loop. And theta is that angle between magnetic field and the area vector. When that angle is 0, cosine of 0 is 1, maximum flux. When that angle is 90, cosine of 90 is 0, no flux. And something in between. And if magnetic flux through the loop changes, okay, actually I want to ask you this question. That will be your last question for this week. Please tell me what you think. Is it a physical question? No. Has nothing to do with physics. It's a purely mathematical question about what possible values a cosine may have. And this is a question which I want to check. Because I would expect 100% correct answers to this question. That's equation number 7. That's equation number 7. My expectation was wrong. You should ask yourself why, because the answer is sometimes it's positive, sometimes it's negative, sometimes it's 0, because if you're calculating a cosine, the value depends on the angle. B in that equation represents the magnitude of magnetic field strength, so it's positive number. A represents the area, but this angle could have any value between 0 and 360. And when you're calculating cosine, you can have any value between -1 and 1. So the answer is sometimes. All right, done. Thank you. Have a nice weekend.
Professor, I have a question. How do you know what direction A is if there's no electric current?
If there is no electric current, because the right chain rule which we use for the area vector assumes that we know the direction of electric current.